Thank you for the invitation to talk at this conference. It's a great honor and it's a privilege, and I'm very pleased to be allowed here to talk about John von Neumann's work. Talking about John von Neumann's work in general is a huge challenge. It's a scarily huge challenge, simply because his work is enormous, both in extent and in depth. So I do not really hope to be able to meet that challenge in a very substantial manner, but I'm trying to do my best, and I'm going to try this according to this schedule and outline. First, I'd like to say a couple of words about von Neumann's work in general, what type of work it was. These will be very general comments on von Neumann's work in general. And then saying something about von Neumann's attitude towards the Hilbert program. And this will be followed by some comments on what he did on the mathematical foundations of quantum mechanics. And in the second part of this talk, I will let von Neumann's contemporaries, colleagues, talk about what von Neumann did together with them on several issues in several fields, like the Manhattan Project. Hans Bethe will be speaking. I copied short video clips from the von Neumann documentary, which was prepared by the American Mathematical Society after von Neumann's death. And I will let Hermann Goldstein talk about the Institute of Advanced Study Computer Development, and Oscar Morgenstern about von Neumann's work on game theory. And finally, we will hear how Strauss, the chairman of the Atomic Energy Commission, talks about von Neumann as the advisor to the US government. This is the plan. I'd like to start by quoting another Hungarian-born famous mathematician, Peter Lax, who writes in the foreword to the John von Neumann selected letters, which has already been mentioned, which I had the pleasure to edit, the following. To gain a measure of von Neumann's achievements, consider that had he lived a normal span of years, he would certainly have been a recipient of a Nobel Prize in economics. And if there were Nobel Prizes in computer science and mathematics, he would have been honored by these too. So von Neumann should be thought of as a triple Nobel laureate, or possibly a 3.5-fold winner for his work in physics, in particular quantum mechanics. Quite serious words about a fellow mathematician. Peter Lax knew von Neumann personally. When Peter Lax moved to the US, he was introduced to John von Neumann. I also would like to quote from a possibly less well-known source, from the transcript of the hearings before the Senate of the Joint Committee on Atomic Energy. John von Neumann was interviewed by the Senate because he was appointed after the war as one of the Atomic Energy Commissioners, and that required confirmation by the Senate. And one of the senators, Senator Jackson, says the following about John von Neumann. I hope that your fertile mind, which is an invaluable resource of our country's security, will be used wisely by this country so that the full scientific talents which you possess can be fully exploited. I sincerely believe that our future security may well depend on the extent to which we exercise good judgment in using your scientific know-how. From what I know of your past record, it would indicate not only the great scientific and mathematical genius that you possess, but to my knowledge, a very unique arrangement that goes with it, good common sense and good judgment. These remarks by Senator Jackson, I think, are very important and indeed show that von Neumann was extraordinary, not in the sense only that he was a scientific genius, but that he had something else in addition to that, which doesn't fit well our stereotype of a great mathematician. the stereotype of a great mathematician is that he's a great mind, his analytic skills are extraordinary, but when it comes to practical, everyday matters, he's quite lost. He doesn't know what to do, or if he thinks he knows, but he doesn't. But for Neumann, it was very different. He, in addition to being capable of analyzing things in a very clear manner, systematic manner, he had an almost engineering-like attitude towards practical matters and also to everyday matters. And this is why he was sought after very extensively as an advisor. And if you ever have a look at the von Neumann's selected letter volume, you will see letters there in which he expresses his views in response to questions about all sorts of issues, like what would be a good place in a university structure of a computer science department? What should be the training of engineers like at Harvard University? What kind of arrangements should an institute like the Institute of Advanced Study put in place in order to regulate the working times of the scientists? All sorts of everyday managerial issues, and he was very willing to give advice, and we will see how this advice was appreciated by those who received them. Now, to von Neumann's work, properly speaking. When you have a look at what he did, then you see that there are two strains of his work. On the one hand, there is the abstract axiomatic one, and on the other hand, there is the very concrete and opportunistic one. The abstract axiomatic includes his work on axiomatic set theory, which was his PhD work, his work on the Hilbert program, and then his work in different subfields in mathematics, like measure theory, ergodic theory, about which we are going to hear later from Professor Sass, lattice theory, continuous geometry, spectral theory, topological algebras. I'm going to say a bit more about these things, foundations of quantum mechanics, and game theory. His work in these areas is very abstract and axiomatic. On the other hand, his work in computer development, numerical analysis, weather forecast, detonations, directed detonations in particular, weapons design, simulations and modeling in general, and consulting and advice is very concrete, very opportunistic, very down to earth. So there are these two strains in von Neumann's work, easily distinguishable. And what is remarkable in addition to that there is a great harmony between these two strains, by which I mean that his work in abstract mathematics is very non-speculative in some sense. We will see in what sense a bit later. It is informed, motivated, influenced frequently by science, by the problem situations in the sciences, by the potential application in the sciences, and by real-world problems. On the other hand, the concrete, the opportunistic work is influenced by the abstract thinking, by the abstract results, and this will become also, it is very clear when it comes, for instance, to the computer development. So two strains in general of von Neumann's work, the abstract, axiomatic, concrete, and opportunistic, but these are in great harmony. They influence each other in a very fruitful manner. And that, I think, is quite unique. I'm not aware of any mathematician or any scientist who would have embodied this kind of harmony to the extent he did. Okay, now I'd like to talk about some of his work in some specific fields. Von Neumann wrote his PhD on axiomatic set theory. Approaches to axiomatic set theory were motivated by the crisis in mathematics at the turn of the 19th to the 20th century, which were prompted by the famous paradoxes in naive set theory, for instance, the Russell's paradox. So von Neumann wrote his first substantial papers on axiomatic set theory, and a closely related problem or issue which was motivated by the paradoxes in naive set theory was the Hilbert program. Hilbert came up with the idea of somehow designing a language which is expressive enough to state all mathematics in it and show that in that language, in that logic, contradictions cannot be derived. Roughly, in a nutshell, this is the Hilbert program. In von Neumann's work, the Hilbert program is the following. Hilbert came forward with the following ingenious idea to justify classical pre-intuitionistic mathematics. Even in the intuitionistic system, it is possible to give a rigorous account of how classical mathematics operates. That is, one can describe how the classical system works, although one cannot justify its workings. It might therefore be possible to demonstrate intuitionistically that classical procedures can never lead into contradictions. It was clear that such a proof would be very difficult, but there were certain indications how it might be attempted. Had this scheme worked, it would have provided a most remarkable justification of classical mathematics on the basis of the opposing intuitionistic system itself. And von Neumann himself worked on the Hilbert program. He tried to accomplish it. But as it turned out, this program could not be accomplished. The turning point in the Hilbert program was the famous Königsberg conference in 1930 between the 5th and 7th of September, which von Neumann attended. He was one of the three major speakers who were addressing philosophical problems of mathematics. The other two speakers were Rudolf Carnap, the leading figure in the logical positivist movement in Vienna. The conference was organized by the logical positivists, by the Vienna group and the Berlin group. Carnap was talking about the logical approach to logicism, the logical approach to mathematics, which attempted to reduce mathematics to logic. Heiting, the intuitionist figure, was talking about intuitionism, and John von Neumann was talking about the Hilbert program, essentially. And it was in that conference that Gödel announced the first incompleteness theorem, which von Neumann got interested in immediately. He pressed Gödel for further details. And a couple of weeks later, when he returned to Berlin, von Neumann at that time was a Privatdozent in Berlin, he wrote the following letter to Gödel. Dear Mr. Gödel, I have recently concerned myself again with logic using the methods you have employed so successfully in order to exhibit undecidable properties. In doing so, I achieved a result that seems to me to be remarkable. Namely, I was able to show that the consistency of mathematics is unprovable. When is your paper going to appear? The paper which is containing the first incompleteness theorem. And when are proof sheets going to be available? This is also of technical interest to me, as I would like to follow you as closely as possible, both substantively and notationally, and on the other hand, I would like to publish as soon as possible. Hoping for your answer by return mail and to see you again very soon. So von Neumann, in today's terminology, proved independently what is called the second incompleteness theorem of Gödel. And the reason why we call it the second incompleteness theorem of Gödel is because, unfortunately for von Neumann, by the time Gödel had received von Neumann's letter, he had already submitted his paper containing the second incompleteness theorem. And he wrote this to von Neumann, to which von Neumann replies in this letter, essentially a week later, November 29, 1930, "Many thanks for your letter and your reprint. As you have established the theorem on the unprovability of consistency as a natural continuation and deepening of your earlier results, I clearly won't publish on this subject." And he never did. He really never did. He regarded Gödel as being an exceptional figure in the history of logic, compared him even to Aristotle, and he says logic will never be the same again. Neumann continues, Thus, I think that your result has solved negatively the foundational question. There is no rigorous justification for classical mathematics. What sense to attribute to our hope, according to which it is de facto consistent, I do not know. But in my view, that doesn't change the completed fact. A quite remarkable moment, both in the life of Neumann and also, I think, in the history of mathematics, when the leading mathematician of the age, in view of these two theorems, especially of the second one, which he himself also proved, to the question, what is your reason to believing that classical mathematics is okay, he says, I have no idea. Quite remarkable, I think. Von Neumann also expressed this view, namely that the incompleteness theorems of Gödel mean the end of the Hilbert program, in another letter from which I would like to quote, which he wrote to Rudolf Carnap about half a year later, in which Carnap and Neumann discuss the proceedings of the Königsberg Conference. And then von Neumann says, I'm today of the opinion that, first, Gödel has shown the unrealizability of the Hilbert program, and second, there is no more reason to reject intuitionism. And he adds to it, which I think is remarkable. I hope there are not many intuitionists here in the room. He says, if one disregards the aesthetic issue, which in practice will also for me to be the decisive factor, saying essentially that intuitionism is ugly, and I'm not going to follow it because it binds my hands, and I'm going to proceed in my mathematical research on the assumption that classical mathematics and pure existence proofs, for instance, are okay as long as someone displays a contradiction in the foundations. Therefore, I consider the state of the foundational discussion in Königsberg to be outdated, for Gödel's fundamental discoveries have brought the question to a completely different level. I know that Gödel is much more careful in the evaluation of his results, but in my opinion, on this point, he does not see the connections correctly. I would like to emphasize nothing in Hilbert's aims is false. Could they be carried out, then it would follow from them absolutely what he claims. But they cannot be carried out. This I know only since September 1930. Another remarkable part of this letter is, which is a separate story, namely that von Neumann says here that Gödel views his results slightly differently. Gödel didn't think at that time that the incompleteness theorems are a death spell for the Hilbert program. Gödel was much more careful, but later on he changed his mind and he accepted essentially von Neumann's position. And it's an interesting question to which I don't really have the answer, why von Neumann and Gödel at that time disagreed so strongly, but there is evidence that they disagreed very substantially. So this is von Neumann's story with respect to the Hilbert program, very abstract mathematics. And from the failure of the program, von Neumann drew a very strong conclusion. Namely, he took the position that mathematical rigor is not a priori, it is historically changeable. Quote from a paper which is von Neumann's only paper in which he explicitly addresses philosophical issues related to mathematics, The Mathematician, Collected Works, Volume 1, if you're interested. He says there, the variability of the concept of rigor shows that something else besides mathematical abstraction must enter into the makeup of mathematics. And he adds to this that some of the best inspirations of modern mathematics, I believe the best ones, clearly originated in the natural science. So von Neumann, partly as a result of the failure of the Hilbert program, embraces a concept of mathematics or a view of mathematics, if you want to call it a philosophy of mathematics, you might want to do that, which is empiricist to a large degree, which is a bit surprising in view of his very abstract work on axiomatic set theory, but this is the conclusion he came to from the 1930s on. So he views mathematics not as something a priori, but something which emerges from our dealing with nature and with society as well. And when we are intending to describe nature and social phenomena in a quantitatively precise manner, we are led to creating mathematical concepts which are suitable for that. This is how mathematics, in his view, emerges. This is a view of mathematics which was not shared very widely, not even by his close colleagues. It is very well known that Wigner, for instance, had a different view of mathematics. On the basis of von Neumann's empiricist-leaning mathematical concept, it's not surprising, is it, that mathematics is applicable in natural sciences, because it's coming from there. How could it be otherwise? It's not at all surprising. Whereas Wigner famously said that the applicability of mathematics in the natural sciences is very close to a mystery which we cannot explain, and he added, which we also do not deserve. So this is not an easily embraceable, not an easily acceptable position, but that was his position. And this position influenced also his mathematical work. And this is what I meant by his even abstract mathematical work not being speculative. A lot of what he did in abstract mathematics was motivated by the problems in the sciences or by the problems of the social world. Quantum mechanics and game theory are prime examples of this, and I'm going to talk about this a bit later. But before then, one more quotation which I think is interesting, because it is a sort of advice which is still valid today for practicing mathematicians, and I do see some practicing mathematicians here in the audience. Von Neumann's empirical attitude towards mathematics includes the following advice. As a mathematical discipline travels far from its empirical source, or still more, if it is a second and third generation only indirectly inspired by ideas coming from reality, it is beset with very grave dangers. It becomes more and more purely aesthetizing, more and more purely larpular, and this need not be bad if the field is surrounded by correlated subjects which still have closer empirical connections. But there is a grave danger that the subject will develop along the line of least resistance, that the stream, so far from its source, will separate into a multitude of insignificant branches, and that the discipline will become a disorganized mess of details and complexities. In other words, at a great distance from its empirical source, or after much abstract inbreeding, a mathematical subject is in danger of degeneration. Whenever this stage is reached, the only remedy seems to me to be the rejuvenating return to the source, the re-injection of more or less directly empirical ideas. Very clear talk. It's a kind of advice for mathematicians to be aware of a danger which he regarded as a great danger. A prime example of von Neumann's work, which was motivated by the empirical sciences, is his work on the mathematical foundations of quantum theory, which I'd like to talk about now in the next part. His work on the mathematical foundations of quantum theory consists of two periods. The first period is between 1926 and 1932. The 1926 is the year when von Neumann goes to Göttingen to work as Hilbert's assistant on the Rockefeller Fellowship, apparently with the intention of pursuing the Hilbert program further. And 1932 is the year when his famous book on the mathematical foundations of quantum mechanics is published by Springer University. But when von Neumann arrived in Göttingen in 1926, in that academic year, Hilbert was lecturing on the mathematical foundations of quantum theory. And it was customary at that time that the assistant of the professor was sitting in the lecture, took notes, and on the basis of these, they made joint publications. And this is what happened also to John von Neumann. And they, Hilbert, him, and another assistant, Nordheim, wrote a joint paper on the mathematical foundations of quantum mechanics. It was published in 1926. And this was a remarkable paper for two reasons, at least. First, because that was the first attempt to axiomatize quantum mechanics. Remember that quantum mechanics was being born around this time. It was a very fresh, young discipline at that time. And this paper was an attempt to axiomatize quantum mechanics. That was the first attempt, and it was published in the Mathematische Annalen, which was the leading journal in mathematics. So the first remarkable thing about the paper is that this is the first axiomatization. The second remarkable feature of that paper is what is at the very end of the paper, in which the authors say that, I'm paraphrasing, not quoting, we are not entirely sure that what we are doing here makes sense, but it's mathematically meaningful. This is what they explicitly say, which is, I think, quite surprising. And then they also say that we hope to return to some of these issues in later publications, and they refer to a forthcoming paper by John von Neumann on mathematical foundations of quantum mechanics. And von Neumann published then, after this joint paper, 3 papers in which he was the sole author, in which he worked out what we call the Hilbert space formalism of quantum mechanics. And I'm summarizing this here. In today's terminology, I'm not entirely faithful to the original system and terminology here. The main point is that it is because of von Neumann's work in the 1920s on the foundations of quantum mechanics that we think of quantum mechanics today as non-commutative probability theory. What this means that the classical concept, the concepts of classical probability theory, which are in blue on the left-hand side, are replaced by quantum counterpart. There is a very strong correlation, a very nice analogy between classical and quantum probability theory. Classical probability theory is a triplet, essentially. You have the set of elementary events. You have a certain set of subsets, a set of certain subsets of the set of elementary events, which is a Boolean algebra. In general, it's a sigma field. And the probability measure is a map on that sigma field into the 0-1 interval. That gives you the probability. Random variables, which are defined on the set of elementary events and, say, take values in the set of real numbers, are measurable functions, and there is a particular type of them which is the bounded measurable functions. The quantum counterpart of these concepts, instead of a Boolean algebra, you take the lattice of projections of an abstract Hilbert